We're going to talk about how safe is Barbie, and that's going to involve us talking about making a scatter plot on the TI-83 or 84. It's going to involve us talking about doing a Duff's analysis of that scatter plot and also exploring the effect of outliers on a given scatter plot. So let's go. Here's some data. A team added some rubber bands to Barbie's feet and dropped her to see how far she would travel in distance. And so we've got some data here. 0 rubber bands was 12, 1 was 14, 2 was 17, et cetera, down the line. Now, as we look at this data, what we're going to do is we're going to use, it says to use Stamplet, but I'd like to actually talk about the TI-83, 84 instructions for a scatter plot. Okay, so the first thing that we need to deal with is the data. So the data input. Data input looks like this. You're going to go to Stat, and you're going to go to Edit, and in L1, you're going to put number of rubber bands. Okay, so Stat to Edit, L1 is number of rubber bands. That's going to be your explanatory variable, your X variable. Your L2 is going to be your distance traveled. Okay, so distance traveled on L2. And that now you have your data. So your calculator has your data in there. The next thing that we need to do with our calculator is ask it to do some calculations for it. So calculation of R value. Okay. The high likelihood is this. The high likelihood is you probably don't have your diagnostics on. And so when you run a linear regression, which is what we're going to do, you're going to run a linear regression, it's not going to spit out the R value or the R squared value unless you turn on your diagnostics. Now, some of you may already have that on, but I'm going to roll through how do you turn on your diagnostics. So you're going to go second, and you're going to go to catalog. And in your catalog, you're going to find diagnostics. Oops. Got to spell diagnostics. Diagnostics on. And you want to hit enter. That's going to populate the diagnostics on function on your home screen. And then you're actually going to hit enter again. And it's going to say done. Okay, and when it says done, that means you've turned your diagnostics on. And so that's the first part of calculating your R value. I'm going to shrink this down because I've got some more things to say here about this and I ran out of space. So your diagnostics are now on. And to actually calculate, so to calculate, what you're going to do is you're going to go to Stat. You're going to go to Calc. You're going to go to lin reg, and it'll say A plus BX. And you want to make sure that your X list is L1 and your Y list is L2. And these are the TI-84. And on the TI-83, it's going to default to L1X, L2Y, and so you should be okay for that. If not, after the parentheses, you need to put in L1, L2. And when you do that, you're going to hit enter, and it's going to spit out your R value, and it's going to look something like this. It's going to look something like this. So I ran my linear regression, and what I got was a correlated value with my R squared and my R value of 0.992. And so let's put that in here. So that's a 0.992. Question number 3 says, how safe do you feel with Barbie's bungee jump if we use this data? So if you wanted to make a prediction moving forward and you have a correlation of 0.992, how safe do you feel? Well, I would feel very safe. Here's why. It's a strong correlation. Okay? And so the question then becomes, what happens if we sneak in some data? Okay, so we sneak in some data like a 15 and a 49, and then like a 6 and a 6. And so to do that, or to understand what the effect would be, We actually have to look at the graph. And so if I look at this graph here, I notice a strong linear pattern, which is great. That is consistent with what my R value said. But the problem is what I'm going to be doing is I'm going to be adding some data values in here. And so when I add some data values in here, I'm going to be adding one way out this way at 15, but also pretty high up on my graph. So I'm going to be kind of out and up. But my 6 and my 6 is down below all of my data values. And so I want to kind of figure out a way to show this to you. So I have a general graph that sort of looks like this, right? And some data points. And so I would hope that you don't write necessarily these steps in there, but maybe sketch your graph. So I generally have data that looks like this, right? Let me zoom in. And in this part 4, I'm going to add one that's way out this way, but also way up here, and it kind of produces one here. So this is, let's let this equal 15 and 49. In part number 5, it's having me add one that's like at 6, but also 6, so it's down here. So the 2 points in question are one that kind of follows the trend and one that's sort of an outlier down there, right? Do you see kind of where I'm at with this? And so the question in number 4 and number 5 is really what happens when you put one in the pattern, what happens when you put one out of the pattern? And this is how it works. Outliers in pattern strengthen the correlation. Because there's a baseline assumption that if the line kept going, they would be close to the line, x and y, so as x increases, y increases. One accidentally left off a digit, so that's how we end up with the 6 and the 6. So how do I think it will affect it? So outliers out of pattern weaken correlation. And that's a good general rule for us to talk about. So let's talk about that scatter plot for just a second here. I see this was my original scatter plot, right? So I'm kind of over here. My original scatter plot, let's do a little Duff's analysis just as a review on that. So Duff's is direction, unusual features, form, and strength. Direction, unusual features, form, and strength. So what would you say about this? If we know that it's 0.992, we would say that is a strong, positive, because it's going up and to the right, linear pattern. Doesn't really have a whole lot of unusual features. So we'd say a strong, positive, linear pattern for that particular scatter plot. Now, down here, unfortunately, the group had measured the lowest point of Barbie's head in inches instead of centimeters. To fix this, they multiplied inches by 2.54 because 1 inch equals 2.54 centimeters. So how do I think these changes will affect the correlation? Verify by calculating the correlation in the applet. So you could do that, but let's just think through this for just a minute. Let's just say we took this and we multiplied all of our distances traveled by 2.54. So this one got multiplied by 2.54, this one got multiplied by 2.54, by 2.54, 2.54, 2.54. So now I'd have something that looked like this. All of them went up the exact same amount. Check out my line here. Does that affect my correlation? Does it affect how strongly they are correlated, meaning how close they are together? And the answer I hope that you come up with is no. So it won't change. The strength of correlation because the points don't move away from each other. They move, but not away from each other. Okay, they don't move away from each other. So the general principle that we can pull out of this is changing units does not change R. Okay, so changing units does not change R. R would still be equal to 0.992. All right, so that's the basic gist of introing what it looks like to do a Duff's analysis, how to put it into your calculator, and how do outliers affect a given scatter plot. Now, a big deal in this section is being able to put your data in your calculator, and we'll walk through that here in just a minute, but being able to put your data in your calculator, find that R value, and work through the process of interpreting it based on the R value, and finding what is that Duff's analysis for this particular data. So let's talk about this. We're going to go at it from the angle that you know the R value. So the big ideas here would be when we interpret R value, when we interpret the R value, it's talking to us about direction. And the direction is going to be positive or negative. And the direction positive is going to go up and to the right, and negative is going to be down and to the left. And the form, we're looking at it, it's always compared to linear. So if you're talking about R value, you're comparing it to linear. So is it linear or not? How strongly linear is it? And it's going to tell us about strength. So it's strength as it pertains to it being linear. And our R value goes on a spectrum with 0 in the middle being weak. And as we move out from there, a positive 1 would be strong. So it'd be like a very strong positive. Anything that is close to that 0.5 or between 0.5 and 1, we could say something like moderate. Okay? But it also goes the other way. And so if we have a negative 0.5 down to a negative 1 would also be strong. But it'd be a strong negative linear pattern. And this would be moderate here. Okay? And so that's our kind of spectrum here. Anything in between, as with statistics, we always want to use LY words. Relatively, fairly, extremely, those kinds of things. All right, second box here, we have 3 boxes. When we're talking about correlation, R does not have units. Okay, R does not have units. And if we switch axes, it does not change R, because the values are still as close to each other as they were. And when we talk about outliers, I'm going to shrink these down here. Oops. When we talk about outliers in pattern, that's going to strengthen. And outliers out of pattern are going to weaken. Okay, so if the outliers are in pattern, they're going to strengthen. Out of pattern is going to weaken. And not the most important thing, but a very, very important point to pull out of here, correlation does not equal causation. Okay, correlation does not equal causation. So just because something is highly correlated doesn't mean one thing causes the other. Okay, so we're going to do the check your understanding here. And I would love for you to try this on your own. And as you're looking at the check your understanding, a good way to do that would be to pause the video right here. Try it on your own and then come back and listen to what I have to say about it as we walk through the answer. So pause here and try it and then come back. Okay, check your understanding. Most people love chocolate for its great taste, but does it also make you smarter? A scatter plot like this one recently appeared in the New England Journal of Medicine. The explanatory variable is the chocolate consumption per person for a sample of countries. The response variable is the number of Nobel Prizes per 10 million residents of that country. Interpret a correlation of R equals 0.791. So remember, on our scale, if we're -1, -0.5, 0, which was weak, up to 0.5, and then to +1. As we get toward the ends of the spectrum, that's strong. So where does that fall? Well, so 0.791 would kind of fall in the closer to 1 sort of thing. So what we could say is there is a moderately strong positive linear association between chocolate consumption and Nobel Prize winner. Okay, so there's a moderately strong, and you can see that, right? So you look and it goes, it's a moderately strong. You've got some outliers here and those sorts of things, but in general, there's a moderately strong association between chocolate consumption and Nobel Prize winners. So if people in the United States started eating more chocolate, can we expect more Nobel Prizes to be awarded to residents of the United States? Explain. So this is kind of a referendum on myself, right? So I want to get smarter. Is my answer to go down to the store and buy a bunch of chocolate and start eating it? That's the question they're asking. So if I, Joe Guy, Phil Saris, started consuming more chocolate, would I be more likely to win a Nobel Prize? Obviously, no, because correlation does not equal causation. Okay? One variable does not explain or change the other. Okay? So let's look at Switzerland. What effect does Switzerland have on the correlation? So let's check out Switzerland here. So think about it for a second. It's one of two choices, right? How does it, well, it's one of three choices. Does it increase the R value? Does it make it a stronger correlation? And why are we asking about Switzerland? Well, it's sort of, it's kind of out here, right? So it's pretty high on the chocolate consumption per person, and it's very high, if not the highest, I think it's the highest on the Nobel laureates. So we would consider this a potential outlier. And so what does it do? So it can do one of three things. One, it can strengthen, two, weaken, three, no effect. And as we talked about above, if it's in pattern, it's going to strengthen. If it's out of pattern, it's going to weaken. If it weaken, and no effect would mean it has no effect on our R value. Well, check it out. As we draw this general line up this way, it's in the pattern, right? So it's as the number of the amount of chocolate consumed went up, its amount of Nobel laureates went up, and so we would have to say it's going to strengthens because it follows the pattern. Okay, it strengthens it because it follows the pattern. All right, guys, so that's the basics of displaying relationships and talking about correlation in R values.